Hi everyone, welcome back to class. So last time we talked about a greedy algorithm, and basically we talked about a Dijkstra's algorithm for finding the shortest path, and also the cruise-path algorithm for the minimum spanning tree problem. Basically today we are going to continue to talk about greedy algorithm, but I think we are going to talk about different domains. So in the past two lectures, we have been really talking a lot about graph problems, and I think basically, this course is in general about algorithm design, complexity, algorithm analysis, and complexity theory. So I guess we should also talk about like algorithm relevant to other domains. Okay, so before I talk about like the contents of today's lecture, I think you probably have noticed that assignment one has passed, and I guess hopefully all of you have submitted the homeworks. And I think for assignment two, we will basically upload the problems tonight. And I think because previously there was a National Day break, so I designed the assignment two to have deadline like 3 weeks from now. And I think currently we are actually having a shorter holiday, but I think I didn't change the schedule, so the assignment two will actually do still in 3 weeks, and the homework, the problems will be uploaded tonight. Okay, so let's talk more about the algorithms. So the intuition, as I just mentioned, is that we want to move from graph problems to more general classes of problems. So the first problem that we will talk about today is the interval scheduling problem. Okay, so what is the problem that we concern here? So basically, in general, for scheduling, I mean, this is very helpful. I mean, in your like course study, I mean, when you go to work, I mean, there are always this such kind of scheduling problem. So let's, for instance, talk about the problem, the interval scheduling problem that we are interested here. So the definition is that we have a sequence. Let's say a sequence of n requests. So where the th request corresponds to an interval. I mean, of course, I mean, for if you want to talk about scheduling problems, there are like can be a lot of different kinds of things that you want to make a schedule. But I think it is quite common that you consider maybe you have like an interval of events. So for this interval of times, so we say that it probably starts of the time. We say that it starts at like a time, maybe SI. So this S just represents start and finishing at TI. This T just represents like terminate. So we use S and TI to represent the starting and like ending time of the event. So here, all the I are taken from N. So in this course, we write this notation to just as an abbreviation of all the integers from 1 to N. So if there is no confusion, just write like a bracket here with N here to represent all the integers from 1 to N. So let's, for instance, maybe take an example. So maybe, for instance, it can be something like this. So this is like the starting time of the first event, and this is like the ending time, the termination time of the first event. So there is like a time interval, maybe for instance, like originally starts at time 0, maybe time 1, time 2, time 3, time 4, time 5, and 6. And maybe this is your T2. And for instance, maybe your, let's say, T3, and maybe your this is the S3, S2, unlike S4 and T4. So it's just something like this. So we have like a time axis. I mean, you have this time, and you have some things that you want to finish. And basically, for such scheduling problem, we assume that an event is represented by an interval. And the interval is actually determined by the starting time and the ending time. So of course, there are actually a lot of events here, and you see there actually some events here are in overlap. So probably you cannot finish them at the same time. So we have like a further definition here. So we say a subset of requests we say is compatible if no two of them overlap in time. I mean, here we make a further discussion that basically, for instance, maybe let's look at the first event and the fourth event here. So actually, I mean, by overlap here, I mean, they really have some like non-zero intersection. I mean, intersection at the boundary, it is allowed in our study here because, for instance, you can, after you finish the first event, you just, right after that, you do the fourth event. So basically that is fine. So here by overlap, I mean, we are okay, let's say, with boundary. Overlap, but not inside. And I mean, if you think about like interval scheduling in general, about like some tasks, like events you would like to finish, and I think it is very natural that the goal here is that you want to accept as large or compatible subset as possible. Okay, so any question about the problem setting? Is this clear? Okay, so let's talk about this interval scheduling problem and basically a good strategy about how we can actually find such kind of a good compatible subset such that it is as large as possible. So let's think about, I mean, you can just like brainstorm a little bit and maybe you can think about what is like a good strategy for solving this problem. I think because we are talking about like greedy algorithm in general about the idea of being greedy. So maybe let's say how to propose a greedy algorithm for this problem. So when you brainstorm, I think you probably need to think about, I mean, as we talked about last time, I mean, we want to talk about some greedy algorithm, but what is the place of being greedy? I mean, if you think about, I mean, this kind of interval scheduling problem, what is the point that you can make it to be greedy? And for instance, you can design a certain algorithm. So maybe you can think a little bit more. Maybe let me actually pause here for 1 or 2 minutes and you can think about like, what is the point that you would like to choose to make it? Sure. More events. I mean, in this specific problem, we don't count on like how long your interval is. So probably you won't want to pick the interval that is super long because that may actually circumvent you from picking others. Here we count the number of events that you like to pick. So maybe let's begin with a few attempts and let's see whether they're actually good or not. So maybe the first thing is that, I mean, you have these kind of intervals. So maybe a very first thing and actually a natural thing that you can consider is that maybe you always want to maybe select the earliest interval. I mean, select interval that starts the earliest. I think, or mathematically, it just means that the one with the smallest SI. So this is something very natural. I mean, at the current circumstance, you have some intervals left, and you can feel free to maybe select interval that starts the earliest. But do you actually think this is a good strategy, or maybe not? So what is the potential issue with this strategy if it is not? Or maybe if this is really a good greedy strategy, can you actually give a good proof for this? So why it is not a good one? Exactly, exactly. So basically, thanks Bohan for giving the example. So basically, this can be actually very suboptimal. So this is not really good. So as it is suggested, so basically we can consider such kind of. So maybe you have an event that starts, although it starts early, that it really takes a very long time, and maybe there are actually some other events, for instance, like this. I guess you can clearly see that, I mean, if you design like a greedy kind of algorithm and you only look at the point that the interval starts the earliest, I mean, you will find this very long interval. I mean, it indeed starts earliest, but this is really not a good strategy. And actually, this is far from being an optimal strategy here. So this suggests that, I mean, you can think about like different kinds of greedy strategy, but at least this very easy way. I mean, you do like select the interval that starts the earliest. This is probably not going to work well. So how about the other strategies? So anyone has a proposal?
So could we just
Okay,
first
so I see you're laughing here. Oh, David, can you hear me? Do you want to say something?
So I think to reach our goal, we have actually two sub goals. One is to first let like the compatible time is the longest. Like we have the longest time for working. That is in this time all the requests are compatible. And second, in this much of time, we can contain like the largest number of requests. So this can reach like the best goal, I think. Yeah, by completing those two sub goals.
I see. So maybe let's wrap up and maybe give like a clear definition here. So you are saying that each time we definitely need to pick an interval that is compatible with the current choices, and I'm probably not quite following. So based on this, what is the next strategy here? I mean, here for instance, I'm taking the one that starts the earliest, but what is your criteria next?
So my criteria is first I want to make sure that like the request like the compatible request I can make a longest list, like it can like contains more like in total of the time like for the request, then
Contain the longest total time.
yeah, and then like in this time I can like if I once I have this time I can like compare in this time how many requests it contains. So yeah, that I don't think I don't know if it's a good idea.
Or contain the longest total time.
And then I just compare like for the numbers of requests in this time.
I see. Oh, I think this is something interesting, and I think yeah, I have I have a few like incoming strategies that I'm thinking about, but I think your strategy is different from mine. So yeah, I think this is a good question. Maybe you can think about offline.
Oh, okay, no problem.
Yeah, but yeah, thanks for the proposal. I mean, yeah, I guess after all, I mean, you probably see the point that in general, when we want to talk about a greedy algorithm, in general, basically we need to have like a cutting point along this, basically a criteria that how we are actually going to design along this and doing this greedily, and hopefully we are actually hopefully we can try to approve some good strategy along that. So maybe let me actually talk about a few other things that is in my mind. So let's for instance, maybe like a second attempt on my side. So second attempt on my side is that, I mean, you probably see that basically for the first attempt, something really annoyed us is that this interval is super long. I mean, this really occupies a lot of things, and it's probably not the best strategy that we can hope for. So I guess a very natural second attempt is that we maybe we want to try to select the interval that takes the shortest time. I mean, I guess this is also something quite natural. I mean, given like the bad thing for the first example is that the interval is super long. Maybe it's probably a natural strategy that we want to each time take the interval that is probably taking the shortest time, or maybe mathematically the interval with the smallest fi minus s9. So is this a good strategy? Right, so this is neither a good strategy. So maybe let's, for instance, think about something like this. So there are two intervals that they are reasonably, I mean, long, but also not super long. But for instance, you have like a short interval like this. So assume that you have this kind of three events. So if you actually choose the shortest interval, this is actually not the best choice. I mean, this interval, although it's short, it really blocks others. I mean, this is not so good. But on the other hand, if you take the two long intervals, actually you can have a better strategy and you can actually finish two tasks. So we have to say that this is also suboptimal. So, I mean, I think along the idea that David just mentioned, and I think also you can probably see that basically based on our first and second attempt, I mean, for this interval scheduling problem, I mean, this compatibility is something really critical. I mean, for instance, you may have the good imagination that taking like a shortest interval can be something good, but I mean, this is really the compatibility that prevents the second attempt to be a good one. So maybe the third attempt that you want to think about is that maybe, for instance, let's select the interval that gives fewest conflicts. So is this a good strategy? So let's consider such kind of example. So assume, I mean, I think the third attempt, I mean, we want to construct something. I mean, if you look at these two examples, it's probably like to select the interval that gives the fewest conflicts. It is actually giving you like the optimal strategy for these two events. But maybe there are some more sophisticated example that, I mean, you want to examine your current strategy along this. So maybe let's take this is like a little bit contrived example, but maybe let's take a look at this example. And maybe, for instance, there are like intervals on this. So let's think about this problem. I mean, what will happen if we insist on like taking the event with the fewest conflicts? So basically, let's take a look. I mean, for instance, like this interval, it actually conflicts with three events. So basically, these three events. And taking like any of these three events, I mean, for the three. So if you take any of these three, it is conflicted with the other two and also conflicts with these two events. So actually it gets four conflicts. And similarly, maybe you can look at this event. I mean, it actually also conflicted with four events. I mean, these three and actually this one. But I mean, you clearly see that this problem has symmetry. I mean, basically it has symmetry, I mean, along the middle of the event. So we don't have to look at the others. So it seems that, I mean, this is the only remaining interval that we haven't been looking at. And actually this interval only has two conflicts with others. So I guess basically by our rule, we will probably have to pick this first event. Sorry, pick this as the first choice in our algorithm. But actually, you can see this is after you choose this interval, this is not giving you the best strategy. I mean, if you choose this one, you cannot choose these two. I mean, on the remaining thing, you probably can only choose this. These two intervals, and this only gives you a strategy that you can pick 3 events. But actually, if you only, I mean, if you look at this by your eye, I guess you can clearly see that there is a choice. Basically, you choose the first one. There's clearly a choice. You can choose 4 events to solve this interval scheduling problem. So still, this third strategy is still suboptimal. Okay, so I think we have been really talking about like a few different strategies. I mean, some kind of greedy strategy that we can use. I mean, it seems that the third attempt, I mean, we select the interval that is taking the fewest conflict. It is probably in general better than the first and second attempt. But in general, this is still not like the optimal strategy. I mean, especially for instance, you consider this kind of construction. So what is the true solution? I mean, if you want to solve the interval scheduling problem by a greedy, what is the best strategy along this? So here, maybe you can see that in general, for instance, when I was talking about a good algorithm, for instance, I was talking about like Dijestra's algorithm for finding the shortest path, or maybe Kruskal's algorithm for instance, the minimum spanning tree. Yeah, you see, like I can introduce this algorithm, maybe for instance, like in a lecture. I mean, basically in 3 hours. But finding such kind of algorithm is not something like very easy. I mean, it really you have some time, and actually there are a lot of failed attempts. I mean, even for this relatively simple, interval scheduling problem, you can still see failed attempts. But maybe let me actually give you the answer here, and let's talk about, for instance, this strategy. So let's talk about a strategy. So basically, we select the interval that what? So this is basically the time that we reveal the answer. And actually, the answer is only 2 words, that finishes first. So, or mathematically, so basically the interval I, for which fi is as small as possible. So we select the interval that actually finishes the first. So let's maybe, for instance, like let's do an examination and see whether this kind of strategy that we select the interval that finishes the first satisfies this property. So let's, for instance, take a look at the first example. I mean, the bad example for the first attempt. I mean, if you choose the interval that finishes the first, I mean, you are first going to pick this. I mean, because this is the interval that finishes the first, and then this one, this one, this one, this one, this one, this one, and the remaining one is actually get conflicted with the other. So actually, we got finished. So how about the second example here? So for the second example here, if you want to pick the one that finishes the first, we are actually also going to pick this one. I mean, this one actually get conflicted with the one at the top. So the only remaining choice is the last one. So basically, this is also giving you a good strategy here. So here for this last example, we can also see that maybe for such kind of basically, I mean, the difference between the third attempt, although it's like a failed attempt, and to our correct strategy that I will actually prove next, is that basically the way that we want to deal with compatibility. I mean, here, if we only like brute forcefully choose the strategy that give you like the shortest conflict, it ultimately is not going to give you so. But actually, it turns out that we are cautious enough. I mean, in this kind of greedy strategy that we, for instance, here, I mean, here we choose the one that finishes the first. We are actually going to choose this one. After that, I mean, look at, I mean, if you choose this one, because it finishes the first, it actually, this 3 is not going to work because it got conflicted with the first interval. But after those, this interval at the top, it is actually the one that finishes the first, and then subsequently this, you're actually going to get a correct strategy for this strategy where you choose the interval that finishes the first. Okay. So hopefully this is clear to you, and I guess maybe let's get into the algorithm and this correctness here. To the algorithm. So here, because we are talking about intervals that we want to make sure that does not have any confliction. So it is very important that we need to make an initialization. So initialize R to be the set of all intervals. Initially, it is the set of all intervals, and we are going to make sure that this is maintained in a sense that we get a correct set here. So while this R is not empty, so we choose I from R that has the smallest fi. So after that, we add this I to the set A. This set A is basically the set we want to output. And of course, we need to give a good maintenance of the compatibility here. So we delete all intervals from R that are not compatible with interval I. So I guess this makes a lot of sense because each time you add a new interval, it suffices that at the time you add that and you check whether this interval brings a confliction with others, and you actually delete them that actually influence the compatibility here. So each time you add a new interval, you just like corresponding check here, for instance, delete all intervals from R that are not compatible with the one you currently added this interval I here. So you just do this algorithm, and actually we have this condition that while R is not empty, you just run this. And at the end, you just return the set A as the set of selected intervals. Okay. So any question with the algorithm and basically the discussion of this strategy? Okay. So I guess, basically for the first, second, third attempts, we can also write down algorithm like this. But after all, we are talking about correct strategies. It is probably fortunate that our current strategy that we choose the interval that finishes the first, it indeed performs well. On these three examples, but they're actually, we need to be very careful, and we are actually going to prove that this is indeed a correct greedy strategy. So observation that we can make. This is actually quite trivial, but actually A is compatible. Or maybe let's do this more formal, that A is actually a compatible set of requests. I think this is just trivial because this is just by the definition how you're actually going to maintain the set R here due to our algorithm. This is a relatively straightforward observation here. But the next thing is not straightforward, and we are actually going to give a proof here. So let's call this a lemma. So let's say that A, the cardinality of A equals to K. If the cardinality equals to K, then the intervals, we can call it I1 to IK to be the set of intervals in A. And I guess we can say that I1 is smaller than I2, smaller than IK. So this is just an output by our algorithm. After all, for this interval scheduling problem, it has an optimal solution. So let's suppose that, optimal solution, let's just denote this by a capital O here. Suppose O is an optimal set of intervals. And let's, for instance, denote the cardinality of O equals to M. So clearly, M is larger than K. I mean, because we say that O here is an optimal strategy. I mean, if you have an algorithm and this algorithm outputs an A here, A is at least a strategy, I mean, due to our observation. So of course, we are going to have, I mean, M is at least K by its optimality. Let's see. And actually, we need to prove M actually equals to Q. So let's prove this. So I mean, for our convenience of making a discussion, so let's also mark the indexes of the intervals in O here. So let's denote the interval, the intervals in O to be, let's say, like a J1 to Jm, because we have denoted the cardinality of O to be M. So where J1 is smaller than J2, smaller than Jm. So this is just a notation thing. So I guess basically we want to give some proof here. I mean, basically we want to prove that our strategy is actually working correctly. So here I think we basically need an assumption. Without loss of generality, we say one smaller than Fn. I mean, here we have been really talking hard about like I mean, for instance, like the intervals from A here is like I1, I2, etc. to Ik. I mean, like the intervals in O is basically J1 smaller than J2, smaller than Jm. I mean, if we don't have such kind of like, I mean, rearrangement, it does not make a huge difference. So that's without loss of generality, we can just first assume that it's all the intervals when they are given to you, their indexes are arranged in a sense that their finishing time is basically this ascending order. So like F1 is smaller than F2 and smaller than Fn, etc. And basically we have the corresponding sequences here. So basically, we want to utilize a greedy strategy. I mean, basically, we are using this greedy strategy, and hopefully, this greedy strategy can give you give us some promise about like the output A here. So basically, we consider such kind of things. So basically, we say that to utilize the greedy strategy. So we prove that the finishing time, I mean, for like arbitrary like rth event, I mean, for all are smaller than K. For the rth event, I mean, the finishing time of the ith event is smaller than the jth event. So let's actually prove this. So we prove this by induction. I guess this is, of course, correct when r equals to 1. Because the algorithm is supposed to choose the interval that finishes the first. So I guess this is just correct. I mean, actually, basically in our notation, we know that I1 actually equals to 1. So this is basically correct when r equals to 1. So now assume the correctness for r minus 1, and then we are going to move to the rth event. So what is the thing that we have been talking about? So we have been basically, we assume the correctness for r minus 1. So that is to say that we have fi r minus 1 is smaller than f j r minus 1. And basically we have something like this. So assume that this is I r minus 1. And then basically you have like a j r minus 1 like this. So since the set O here, I mean, we are taking like an optimal solution here, but since O here is, I mean, it is an optimal solution. I mean, by a solution, it should be definitely compatible. So we know that f j r minus 1 is actually smaller than the starting time of jr. So basically, it's basically looking like that. Otherwise, I mean, if f j r minus 1 is larger than jr, then this is something you get a confliction here. This is then this O should not be actually a solution, which we get a contradiction. So basically, we must know that the finishing time of J R minus 1 is actually smaller than or equal to the starting time of the event JR here. So this is basically saying that basically the finishing time of the IR minus 1 event. So basically this event. I mean, we actually have this result, this assumption based on induction that F on R, Fi on R minus 1 is actually smaller than or equal to F J, Fj R minus 1, and this is actually a smaller than Sj. So what does this suggest? I mean, this suggests that JR is actually available. After the algorithm runs for R minus 1 iterations. And actually by the greedy property. I mean, by the greedy property, we know that based on our argument that JR, this event, is a feasible choice. I mean, after you have to run this algorithm for R minus 1 iterations, it is a feasible choice, but the algorithm picks, I mean, IR instead of JR. So basically, this is suggesting that FIR smaller than or equals to FJR. I mean, I should probably be a little bit cautious. I mean, I was just saying that we pick IR instead of JR, but actually they can be equal. But I mean, at least we know that FIR is smaller than or equal to FJR. So basically, on this finishes our this kind of like the induction. So any question about this induction? But basically, this argument. Any question about this? Okay. So I guess this basically from this argument, we can see the importance of we are actually taking the interval that finishes the first. I mean, this part is really critical that we make the argument work. I mean, basically, we want to have a good way of utilizing the greedy strategy here. And actually, we see that basically assume, I mean, we already whatever, we have an optimal set of the compatible intervals here. I mean, basically, you have because your strategy is taking the one that finishes the first. I mean, this kind of I and J here is always like the J is at least not as early as your greedy strategy. I mean, basically, after you have this kind of greedy strategy to choose that this finishes the first, it's really make the argument work. And basically, we can make the induction going through here. And that is actually the intuition suggests that why this algorithm is actually correct. So the remaining argument is actually quite brief here, as maybe you can probably see next. So now, suppose that K is smaller than M. I mean, here, so basically we talk about that M is actually larger than or equal to K. I mean, let's just assume the case where the equality does not hold. I mean, this optimal strategy is strictly better than the output of the algorithm. And let's try to find some contradiction here. So by the argument above, by the way, I think one thing that I forgot to emphasize about. So here we mentioned that M is clearly larger than or equal to K, and here we are talking about the induction here. So for all R is smaller than or equal to K. I mean, this definitely makes sense because the number of intervals, I mean, the number of intervals in the output of your algorithm is K, and the optimal strategy, this M should be at least larger than or equal to K. So basically, it makes sense. I mean, this induction should, the induction should be able to go at least for K times. So let's take this observation here, and basically by this induction argument, we clearly see that Fik is smaller than Fjk. And actually this suggests that actually Jk is compatible with I1 to Ik. So this is basically the same as this argument, same as this argument. So because we have assumed that K is smaller than M, I mean, this J is at least one longer than this the number of events in I here. So basically, it is saying that JK is compatible with I1 to IK here. Oh, I think I probably made should be JK plus 1. So, however, our greedy algorithm ends with K iterations, a contradiction. So because here in our algorithm, we are saying that while R is not empty, you just run this algorithm in a greedy sense. But basically based on this discussion here, you're suggesting that there exists at least one interval, from all possible intervals that are actually compatible with your intervals, but your algorithm terminates. So this is basically a violation of the greedy strategy and basically finishes the whole argument. Okay, so this basically finishes the proof that our algorithm is correct for this interval scheduling problem. So any question? So any question about the correctness of this greedy strategy? Okay, so if there is no question, let's further talk about, we talked about the correctness and basically this is the correct strategy. Then of course, the next thing is the time cost. Basically how efficiently this algorithm for interval scheduling can be implemented. So basically we say that this greedy algorithm, and let me use this here, can be implemented in time actually O(n) log n. So how do we do this? So sorry. So recall that sorting. Basically by sorting, input. Let's say that basically input all F1 to Fn, sort them. So basically give like a rearrangement about the ordering. Basically you sort them such that F1 is smaller than F2, etc. Basically a sorting takes O(n) log n time. So we will actually this is well known. And actually we will prove this next class. I guess maybe from your undergraduate course, you have heard this result that basically sorting takes O(n) log n time. And I think we have assumed here. And I think basically for the first homework, we have a related problem here. And actually in the next class, we will talk about, for instance, divide and conquer algorithms, and we will talk about merge sort. So we will reprove this, but maybe for instance, in this class, I take this for granted that sorting takes time O(n) log n here. Okay, so basically, because here it is very critical here that the strategy here, we are choosing the interval each time we are choosing the interval that is having the earliest finishing time. So it definitely makes sense at the beginning, we just first sort all the intervals, and basically we give such kind of ordering, and basically then we consider what is next, and we have like a good way to maintain our algorithm here. Okay, so I think not only we can sort, because sorting is like only taking like O(n) log n here. If you, for instance, here we are sorting about the finishing times. We can also sort about the starting times. Such that. So we can also sort about the starting times. This takes another O(n) log n, but does not influence the overall cost. We only do this sorting for twice. So let's think about some a clever way that maybe we can maintain. I mean, basically, from our argument here, I mean, we actually have very briefly mentioned that you can clearly see that I1 should equal to 1. I mean, but actually, there are more observations that we can bring into here. So because basically, let's take a closer look about what the algorithm is actually going to give you. So we select the interval I1 equals to 1. And then, I mean, then we need to select the second interval here. So the second interval here, I mean, we can select, I mean, we can first, we probably need to first figure out something. So I mean, we can set an index. I mean, we can initiate the I2 here. I mean, if you have selected, for instance, the 9th interval, the next thing that you're going to start from the 10th interval. I mean, you have to look at the previous intervals, and actually we are going to do this basically from like ascending order of the finishing times. So here, maybe for instance, for the I2 here, I mean, we select the first, and we only need to check, for instance, like the second interval, the third interval, etc. And actually here we set I2 equals to I1 plus 1 here. So we increase I2 until we reach an I2 such that Si2 is larger than Fi1 and output this. Okay. So what is something that is actually can be directly implied by this sentence? So we increase I2 here until we reach an I2 such that Si2 is larger than Fi1, larger than or equal to Fi1. So basically this is suggesting that for I in the middle, we actually has Si smaller than F1 because we have been trying this. And I mean, here we use observation that I1 equals to 1, but because in the middle we have been trying all these kind of things, but they didn't succeed. So actually they conflict with interval. So basically they got conflictions. So this is the reason that because we have basically sort all the intervals from like ascending order of the finishing time. So we have been really trying all the previous intervals, but unfortunately they actually got conflicted with the first interval. So this is not so good. I mean, but actually we want to make sure that the criteria that we use, because you want to make sure that they are not conflicted by the starting time of the second interval. I mean, basically this sorting is basically for our ease of our life, but actually we clearly see that the I actually goes into the sorting order of the finishing times, but the criteria rule here is, of course, we're checking Si2, whether Si2 is larger than or equal to Fi1 here. And maybe let's go into the next line. So for instance, like we increase, we need to first set I3 equals to I2 plus 1, and we increase I3 until we reach an F3 such that Si3 is larger than Fi2 and output Si3. And we just do this again and again. So the total number of attempts is smaller than n. So basically, we are very careful about the I here we use here. I mean, we have the first interval here. I mean, we choose that, and basically we try the second, the third, etc. until basically we find the I2 such that Si2 is at least larger than or equal to Fi1, and we based on this I2, and then we choose we try I2 plus 1, I2 plus 2, etc. So basically, you see that for this sequence of I's, it's basically something strictly increasing, and basically the total number of attempts that we actually try here is, of course, at most n here. And basically, as you can clearly see, that basically try all these kind of things, and basically for updates, and just take O1 time. And so basically, this is stressing that the total cost. That means this is just ON. And basically, this finishes the argument that the time cost of this interval scheduling problem is n log n. Actually, it is quite expensive at the beginning. I mean, not quite expensive. I mean, O(n) log n is like log n more expensive than ON here. But actually, the main cost is actually based on sorting the finishing time accordingly. Okay, so this basically finishes the argument of the interval scheduling problem. So is there any question about the correctness, about the complexity analysis, etc.? Okay, so if there is no question, let's take a break for 10 minutes.